Hello, my name is Nicholas Adalaglu, and today I'm presenting you our work adapting clip for out-of-distribution detection. This is a joint work with my collaborators from Heinrich Heine University of Düsseldorf, Felix Missels, Tim Kaiser, and Professor Markus Kollmann. So let's start with the task of out-of-distribution detection. And the task of out-of-distribution detection aims at identifying whether a given test sample is drawn from the in-distribution training set or an alternative distribution, which is typically known as the out-distribution. Here, for each individual test sample, we have to decide whether it belongs in the in-distribution, the training data, or the out-of-distribution. Typically, Cypher 10 and Cypher 100 used to be the in and out distribution, but nowadays benchmarks have typically moved to large-scale OOD detection benchmarks, where typically ImageNet is considered as the in distribution, and various OOD datasets have been proposed. In our work, we study how CLIP can be used in all three OOD detection scenarios. First, unsupervised, where only the images are available without any additional information. Second, the scenario where the in-distribution label names are available, and thus CLIP text encoder can be leveraged. And the third scenario is that when the in-distribution label, ground truth labels are available, which is typically referred to as supervised OOD detection. So our key contribution in this work is to study how CLIP models can be adapted for all these three scenarios. We start from unsupervised OOD detection, and we find that the recently publicly available OpenClip model, specifically VIT Giga, has the best unsupervised performance on all the large-scale benchmarks, and even outperforms self-supervised models and supervised models that are trained using on ImageNet. And second, for the scenario where in-distribution label names are available, we propose a new method, which we call pseudo label probing, which allows us to leverage the text encoder of CLIP. And third, for the supervised OOD detection scenario, we benchmark linear probing versus the typically adopted strategy on the field of OOD detection, which is fine-tuning on the in-distribution. Finally, we expose the vulnerability of CLIP models, and specifically the largest publicly available CLIP model, which consists of 2 billion parameters, to adversarial out-of-distribution attacks. So first, we benchmark more than 20 models on out-of-distribution detection measured with the AUROC score. In both cases, in both plots, ImageNet is in distribution. And the out-of-distribution on the left is NINCO, a newly proposed dataset, and ImageNet O, proposed from Hedricks et al. To measure the OOD detection without any additional information for the unsupervised case, we use the top one feature similarity of the test sample to the training split. And for the KNN accuracy, we use the 20 nearest neighbors to classify the in-distribution data, which is measured on the x-axis. Apart from showing that CLIP is the most the CLIP with VIT Vision Transformer Giga is the best performing OOD detector, which is shown with this big blue star. We also find that the publicly available CLIP models have a very strong linear correlation of in distribution classification accuracy with respect and OD detection, where we found an R-square coefficient larger than 92 for various small and large scale OD benchmarks. And the next question is how to apply CLIP when, apart from the images of the in-distribution, we also have the ground truth label names of the in-distribution again. So previously, the baseline we consider, which we call it pseudo MSP, uses essentially zero-shot classification, where, as indicated with the pink color, we provide text prompts using the in-distribution label names to derive text-based representation for each in-distribution class. And then we compute this, we compute the similarity with all the visual features derived from the image encoder of CLIP. So using this vector of image text similarities for each test sample, we can measure OD detection score, an OD detection score such as the maximum softmax probability. We call this baseline pseudo MSP, and on top we propose a new method which we call pseudo label probing, where instead of directly measuring the OD score using the image text similarities, we use them as pseudo labels by simply taking the index that corresponds to the argmax after softmax. So in this case, the photo of the dog, class dog, which is index number 3. It's based on these image text similarities. And we use these pseudo labels to train a linear layer on top of the CLIP pre-computed features, which is very fast. It doesn't need it doesn't require the fine-tuning the backbone features, which requires tremendous amount of resources. And as we will see, it scales very well with large-scale models. After training this linear layer with the strategy called pseudo label probing, or PLP in short, we ablate using 3 different scores. So for all 3 applied on the output of the trained linear layer. So as in pseudo MSP, we consider the maximum softmax probability. And additionally, we consider the relative Mahalanobis distance and the energy score, which are known techniques that have been proposed for supervised OD detection. And we apply them in this scenario where using the pseudo labels. We find that both the relative Mahalanobis distance and the energy score work quite well for pseudo label probing, and we adopt the energy score because the relative Mahalanobis distance requires more computational resources, which is extremely costly, especially in the scale of large-scale benchmarks like ImageNet, while the energy score is computed directly on the output of the linear layer, so-called logits, as shown below. Then we put our method into the test. We consider various large-scale OD detection benchmarks. So each of these 5 shown dataset is the out distribution, and ImageNet is always the in distribution. We also report the results from pseudo MSP and our reproduction with the Dagger from Ming et al., which was the ones that proposed this baseline of computing the maximum softmax probabilities on the image text similarities. And as shown here with the red rectangles, on the large scale publicly available open clip models, we see that our strategy, pseudo label probing, using the energy as the OOD score, consistently outperforms pseudo MSP, the considered baseline. Next, we move to the supervised OOD detection. And we want to see if fine-tuning free approaches, meaning if we can avoid training the backbone, which is quite costly, and if it can be avoided. And here we find also that instead of fine-tuning, we can simply do linear probing. Instead of the pseudo label, we use the real label, since it's now available on the supervised benchmark. And again, we find that energy is the best performing score in the majority of cases, especially on the large scale evaluation benchmarks. Using the publicly available clip models that are fine-tuned on ImageNet, that are available from the TIMM library, we show again the same trend that the larger models seem to be more benefit from linear probing rather than fine-tuning, which is not the way, not the typical strategy that is adopted based on the previous literature on out-of-distribution detection. Finally, we ask the question if ImageNet21K pre-trained models can also work better using this simple probing idea on the ImageNet benchmarks, and we find that at least for the 3 considered models, they seem to work consistently better on the large-scale evaluations using ImageNet as the in-distribution. So overall, we suggest that probing can match and many times outperform fine-tuning on the large-scale OOD benchmarks, which is not always the case on the small-scale benchmarks of Cypher 10 and Cypher 100. Taking a deeper dive into the small data regime and the small-scale OOD benchmarks, we see that using all the vision transformer-based models trained with multiple times of supervision, indicated with different colors on the bars, we cannot identify any consistent behavior between different types of pre-training and different pre-training distributions. And for example, on using Cypher 10 as the in-distribution and Cypher 100 as the out-of-distribution, you see that Dino pre-trained on ImageNet is the best choice. Even outperforms the VIT-based pre-trained on Lion 2B, and no consistent behavior in general can be identified on the small-scale benchmarks. And for this reason, we propose the adoption of we validate the adoption of the large-scale benchmarks, because the small-scale benchmarks don't always translate to the larger scale ones. Finally, we propose a very simple method to derive adversarial OOD samples, where A is the original sample and B and C are the manipulated samples based on an adversarial manipulation, trying to match the features of in distribution images. So we manipulate out of distribution images of specifically Cypher10 in such a way that they maximize the similarity in feature space with the in-distribution features, randomly drawn in-distribution features. Here, for example, we use an in-distribution apple, and we visualize the two different types of adversarial perturbations we propose. And overall, we validate that clip is still vulnerable to adversarial tags, dropping the ROC to the random guess score of 50% independent of how one chooses to quantify the OOD detection score. That's it. Thank you so much. And feel free to check out our TMLR open review page, and the codes will soon be publicly available. Thank you.